Okay, let's get this math done. We'll all go down to the park and have some fun. Hey, welcome to geometry. It's hard to take you seriously with them glasses on, so I'll take them off. All right, geometry. This is the last lesson from our unit that we've been working on. This is lesson 17. We are going to be done, and that means unit test is coming up. So next week, we will have a review lesson. The first part of the week, the Monday, Tuesday lesson, and Wednesday, Thursday will be our geometry unit test. So if you are still catching up on past lessons, this will be a good time to get caught up by between now and next week because you need to know all of that stuff. If you skip some of my videos, you might want to go back and catch some of that too because this is going to be a lot of information. And most of it was online. We didn't get a whole lot done in the classroom when we started this unit. So there should be wonderful videos for all of the things that we're going on this. And like I said, we will review Monday and Tuesday. But let's get to today's lesson. All right. We're gonna look at a few different things today. We looked last time at medians, right, where we found the midpoint of a side of a triangle, connected it to the vertex on the other side, and made a median. And we did that for all of them, and we found that point in the middle that worked for all of them, the centroid, if you remember, the point where the triangle would actually balance. This time, we're going to look at altitudes. Remember, we talked a little bit about the difference between the altitude and the centroid. Today, we're going to look at altitudes instead. So remember with the median, we found the middle between here and we connected that, and that became a median going up to that corner. This is an altitude. All right, an altitude will be straight up and down, the height of the triangle. But all right, let's see what we're doing here. First, find the slope of each side of the triangle. Okay, well, the slope of this is 0. So we got a slope of 0 right there. That's the easy one. There's no rise. Rise over run. The top of the fraction's a 0. The fraction here, let's see, it looks like it goes up 1 over 1, up 1 over 1, up 1 over 1. So that's 1 over 1. So that slope is 1. All right, wonderful. And the slope right here, it starts here and it goes to that point. There's another point it crosses, and then it comes down and crosses this point. So it goes 1, 2, 3, 4, -5. And then over 1 goes -5 and over 1. So it has a slope of -5 because -5 divided by 1 is -5. So that is the slope of the sides. Okay. Now find the slope of each altitude. Well, an altitude, if we have a triangle, the altitude is going to be at a 90-degree angle, right? So from this one's real easy since it's on that point and the bottom is on the x-axis. We can just draw that straight down and say that is an altitude of our triangle because it's at a 90-degree angle. It's going to be perpendicular. And since we know the slopes of these lines, we can find the perpendicular slopes. Now that's having a slope of 0. That would be 0 over whatever the run is. The slope of the perpendicular line would be undefined because we can't turn that upside down and divide by 0. So would be undefined because it's a straight up and down line. We don't have a slope. It's just going straight up and down. Let's see if this one is -5. That means the perpendicular slope, let's turn that over instead of -5 over 1. It's 1 over 5, and it was negative. Let's make it positive. So it's going to be a positive 1/5. So we have undefined, a positive 1/5. Say this was 0, -5, and 1. All right, so now the third one, this had a slope of 1 over 1. If we turn that over, we get 1 over 1. And take the opposite sign. So this is going to be -1. So 1 and -1 are perpendicular slopes. Slope of 1, -1. Sketch the altitudes. All right, I already did that one that has the undefined slope. But this one would have a negative. So I'm going to go starting from this point because that's where the altitude comes from. It comes from that point all the way to the other side. So if I went straight down, if this triangle had the bottom right here. I want to bring this straight down. And I know the slope should be -1. So for every one it goes down, it should go over 1. So we're looking at a line that goes right there. Okay, so our slope is -1 over 1, -1 over 1, -1 over 1. So that is the altitude, which will be at a 90-degree angle to that side. And then we've got this side. If this was the bottom, that altitude there. So starting from that point, let's do our slope. Slope would be 1/5. So it would go up 1 and then over 5. 1, 2, 3, 4. It would go through that point right there. And then it would go up 1, 1, 2, 3, 4. It would go to that point right there. So let's connect these points to make the final altitude. So there are the 3 altitudes of this triangle. All right. Label the point of intersection H. Notice, just like when we made our medians, all 3 altitudes come to a single point where they all meet at. We're going to call it H right there. Write equations for all 3 altitudes. Oh, that's challenging. Let's do that. Okay, so let's start with this one. Okay, this one right here. Now, when I write an equation, I can write their lines. I can write it as y equals mx plus b if I have the y-intercept and the slope. If I don't have the y-intercept and the slope, and I just have the slope and a point, I'd want to use the y minus k, the point slope form, x minus h, right? Where hk is that point I have. So let's see which one's appropriate for each one. For this first one that goes along here, it doesn't cross at a point. It's just below the 1, so that's going to be some fraction. So that's probably not good to write it as a y equals mx plus b, because I have a hard time figuring out what b is. So I'm going to use this one. I know it goes to this point because that is where we started the altitude at, which is -4, 0. So the y is 0, so y minus 0, the k part of our point, the hk, we don't need to put -0, so we'll just leave that as y. We can. It's not wrong to go y minus 0, right? But we're just put y equals, what's next? Our slope. We calculated our slope. It was 1/5. Then we put x minus, what is our h? What is the x coordinate of that point? It's -4. So if it's x minus -4, you subtract a negative, you add. So that is the equation for that line right there. All right, fabulous. So y equals 1/5 parentheses x plus 4. Okay, now let's do the one that comes down. Okay, when it comes down, it's coming down 1 over 1 over 1. I can follow it back up there and find out it would actually touch at 8 because it's on the point every time. It's on a point. So I'm going to do the y equals mx plus b because it has a slope of -1. So it's negative x plus 8. That is the equation for this altitude here. And finally, this last one. Oh, we had some problems like this on our practice problems. It was a lot of fun watching, trying to figure that out. Some folks were getting it. Some were struggling with that. We had problems on our practice problems that said, write an equation that's perpendicular to a line of y equals 4. Well, it would be an up and down line like this. This line would be x equals 6. Right? Because x equals 6 everywhere on that line. This h is at the point 6, 2. H is at 6, 2. So it says use these equations to find the coordinates of h and verify algebraically that they all intersect at h. So if 6, 2 really is the point of intersection, then that point should be on every line. All right, if it's not on one of those lines, that's not the point of intersection. So I can go back to my equation, y equals 1/5 x plus 4. And here's the point. So the y is 2 equals 1/5 times the x is 6 6 plus 4. What is 6 plus 4? 10. So this is the same as 2 equals 1/5 times 10. 1/5 times 10 is 2. Perfect. So this one is on that line. How about let's check the next one? Y equals negative x plus 8. So the y is 2. It's supposed to be negative 6, because that's what x is, plus 8. Does 2 equal negative 6 plus 8? Yes, it does. And finally, the last equation is x equals 6. Does our x equal 6? Yes, it's on that one too. So it is on all three lines, because the equations for those lines, we can take the point and plug it into those equations, and it works on every time. So perfect. That is how we find this. This is called the orthocenter. There's all kinds of names for these points, right? We had the centroid last time. This is the orthocenter. So we'll look at that. Okay, we're gonna percolate on perpendicular bisectors. We're gonna be doing some percolating here. So here is a triangle. It wants us to find the midpoint, the perpendicular bisector, using index cards to make sure they're 90 degrees. Write equations for these. Find the point in the middle of that. Tell you what, we're going to switch. Instead of doing this slowly, I'm going to speed things up a little bit for us. And we are going to do this online. All right, so I'm at GeoGebra. And on the notes, I have the actual web address of this particular page that I'm on. So if we were going to make a triangle, okay, so I'm going to make a triangle. I can just... There we go. There's our triangle. So we have this triangle. Go ahead and make this full screen. So we see this nice, lovely triangle we have. All right, so make it a little smaller. Oops. All right, so we have this triangle. And the next thing it said was to find the midpoint. So I can go up here to points, and there's the thing right here, midpoint. So if I'm clicked on midpoint right there, and I click on this side, it found the midpoint automatically for me. And if I click on this side, there it is. And I click on that side, there's the midpoint. So there is a triangle with the 3 midpoints already marked for us. Now they want us to sketch the perpendicular bisectors. They said, use an index card, make sure you're 90 degrees. Well, I'm going to use GeoGebra to make sure I'm 90 degrees. If I click on this button right up here, this is a perpendicular line. It says right there at the bottom of the screen, perpendicular. So if I make a perpendicular line, right? Oh, wait, I'm not on the right one. Where's it? There it is. Perpendicular line. Is one of these. Oh, there's a perpendicular bisector. Perfect. That's even better. So instead of making a perpendicular line, this will make sure it's right in the middle. So if I click on perpendicular bisector and click on the side, oh, it made my perpendicular bisector for me. So I'll click on this side and finally this side. All right. So we have this point. Now, the interesting thing, if the shape of our triangle is different, and, oh, wait, undo that. I'm getting off. All right. If we move that where it's different, that point would move. Now, it's not moving this line because that is the perpendicular bisector for the bottom, and I'm not touching either one of those points. See, if I move that, it'll change that. So we change our triangle around, it just changes where that point is going to end up. Kind of a cool thing on that. I like that. So use the equations to find the coordinates of P and verify that it is that they all intersect there. We're not going to worry about that because we can see that. We see that they all intersect there. I'm not going to put this on a graph. I think we can get the idea from this. Okay, so looking at this, I want to show you something that's kind of cool. This is the perpendicular bisector, right? So we've done the median. The median came from the midpoint to the opposite corner of the triangle, the vertex. We just looked at the altitude, which starts in that corner and goes straight down to the 90-degree angle. This is the perpendicular bisector. Notice this doesn't go through the points of the triangle. I mean, it could, depending on the triangle, right? If we had this point over here, it would go through that point, right? But ours, as it is right there. So perpendicular bisector finds the midpoint, just like we did for median, but instead of drawing it to that corner, it draws a 90-degree angle. Okay, a 90-degree angle. This is called the circumcenter. So we've had centroid and orthocenter and now circumcenter. Now let me show you why it's called that. It's pretty cool. I'm going to zoom in here where we can kind of get a little closer and see exactly where these points are. All right. There is our circumcenter that we found from the perpendicular bisector. Here is a point on the triangle. Let me switch to circles. So if I go to this circle and I say I want the circle to be centered on the circumcenter. All right, that's about perfectly in the middle. And I want it to be this big out to that point. All right, oh, that jumped a little bit. Let's do it again. I want it to be exactly from that point. Go and jump every time. Go and get me going crazy here. We're going to keep this and whatever it looks like. All right, so we take that to that point right there. Okay. Now, if we go back and zoom back out, let's look at the other points of the triangle. All 3 points of the triangle are on that circle. That's why that's called the circumcenter, because that is, if this triangle is put in a circle, inscribed in a circle, all of those points would fall on that circle's edge, right? Fall on the circle. So basically, it's the same distance from all those points. That circumcenter has to be the same distance from the top point of the triangle, the left point, and the right point, right? Because all of those are a radius of a circle, right? That circle has the same radius from the center. So that point where their perpendicular bisectors meet is the same distance from all 3 points of the triangle. Kind of cool. There's a lot of different things we can kind of do with this kind of stuff. So what we see is there's a lot we can do with triangles that we haven't even touched yet when we start doing these type of things. So let me pull up another page while we're looking at all of this. Right here. Okay, let's make this big. Okay. Here's just a basic triangle. We have looked at the centroid, right? That's where we had these midpoints. D, E, and F are midpoints. And the centroid is where we connected them to the other vertex, right? On the other side of the triangle. We did that and gave us the centroid, right? So that would be that point right there. That'd be like the balanced center. That would be the centroid of the triangle. If we take that off, today we looked at the orthocenter, all right? Remember what the orthocenter was? That is taking the altitudes, right? So from this coming straight down, this would be a 90-degree angle. All right, this would be a 90-degree angle. So these are all perpendicular to the sides from each vertex. So the 3 altitudes, they make what we call the orthocenter. And now we just looked at the circumcenter, which was those midpoints again, right? We had the midpoints that we used for the centroid. We also use them for the circumcenter, but we do a perpendicular 90-degree bisector at those midpoints. And so the circumcenter's up there towards the top of this particular triangle. Now, there's something that's kind of cool about the relationship of all these. If we put the circumcenter on there, and we put the orthocenter on there, and now we're really going to trash it up. We're going to put the centroid also. Look at all them lines. There was a Swiss mathematician lived in the 1700s, and around the year 1765, he discovered, looking at all this kind of stuff, that the circumcenter, the centroid, and the orthocenter of a triangle are collinear. What's that mean to be collinear? Co, it's like share. Usually like you have a co-president or, different things. Cooperate. It's 2 things sharing at least. Collinear. Linear's line. So that means they share the same line. So these 3 things are collinear. Well, since then, hundreds of years later now, it's called the Euler line. And look, we can graph that. The Euler line shows all 3 of those things on the same line. Now, after Euler died, they found a couple of more points that also fall in that line from other things we can do with triangles and inscribing triangles and stuff like that. But these were the 3 that Euler discovered. It's called the Euler line, and they all line up on there. Just kind of a cool thing discovered back in 1765. This works for any triangle. Let's see, does this triangle let me move that point? Oh, it can. Look, as I move the shape, those points all move, but they're still on the same line. Still on the same line. All right, I do want to point out one thing. Let's go back to the ortho center that uses the altitude. All right, I'm going to straighten this up where it's kind of straight at the bottom. We're used to seeing the point in the middle of a triangle, but sometimes, like the ortho center, could be outside the triangle. What do you mean it could be outside the triangle? Well, let's think about the altitude. If this triangle looks like this, or this, all right, the altitude of that, the height, would be measured over here outside of the triangle. We would not take a distance that would go this direction, it'd be straight down. So in this case, the altitude runs there, this altitude runs there, this way out here, so that the point actually moved way outside of the triangle. So, but you can see it as I move it closer to a 90 degree, and look at a 90 degree, the ortho center is exactly on the point where the 90-degree angle is, because this is the height. That is the altitude. It's a straight 90-degree angle. For the other, if we flipped on the side, that is also an altitude. So all of those points in a 90-degree triangle end up right there at the 90-degree angle. So, but as you move it over, it moves inside there. So it could be outside there. So what about the others? Could they be outside? With a centroid going from the median to a point? No, see, that's always going to stay inside because you're connecting the midpoint to a point in the triangle. Centroid won't move outside. How about the circumcenter? It uses the perpendicular bisectors, and look at that, the circumcenter can move outside. So the orthocenter and the circumcenter can both be outside or inside the triangle when you get the longer, kind of odd-shaped ones. When you have more standard triangles, they're usually in the middle. But it's not uncommon at all for those to be outside. Just a little something I wanted to look at today. I want to show you one other thing that this lesson covers. It just barely, I wouldn't say it covers it, it touches. We're going to touch, real quick, a word called tessellations. I don't know if you've heard of tessellations. I had a professor at the University of Arkansas that he was doing a research on tessellations, and he had lots of examples of them. He brought some in the classroom, and we got to kind of try to assemble some to see if they work. But a tessellation is where you take the same shape and you cover a surface with it over and over and over again with the same shape. Let me show you an example. Here's a tessellation right here. This is using these kind of diamond shapes, right? And they're all exactly the same shape. Every one of these are exactly the same shape. They're just turned, and they're put together like a puzzle where there's no space in between them. That's called a tessellation, and that can be done with any number of shapes. It doesn't have to be a square or a rectangle. I saw one up here. There, it's done with parrots. The exact same parrot shape used over and over again to not allow any space in there at all. Monsters, stars, all kinds of ones. I saw one where someone had cats even. There's one that doesn't look like a tessellation. It's using different figures. Oh, here's the one with cats. There you go. Cats, using the exact same cat shape. So this is used a lot in graphics, backgrounds, fake backgrounds, and stuff like that. You'll see that in flooring. When you see tile floors, those are a tessellation. A lot of times, the same shapes over and over again. There can be tessellations that are combination shapes, such as that. So you're using the triangles along with hexagons. And so you have two different shapes you're putting together. So it's just basically a repetition, and it can go on infinitely in math if we talk about a tessellation. But I just wanted to kind of show you that. We're not going to spend much time at all on it, but just wanted to show you what that was. So where are we at? We are at the end of the unit. So if you have not finished any, please do that. We have a short lesson today. You'll have a couple of problems kind of related to what we're doing, and some review problems of stuff we've done earlier, because we need to be refreshed on all that by next week. So do work you can be proud of. We'll see you next week.